I must say, it was a pleasure in setting to see real learning. So what I want to talk about is what we've learned about Pluto since the New Horizons spacecraft flew past in 2015. And if I had to summarize the entire talk in one slide, this is what it would be. On the left, you can see the best image of Pluto that we had before 2015. It's a Hubble image, and it's a few pixels across. And so prior to 2015, we could barely make any features out on Pluto with the best available telescopes. And then after 2015, we have a whole new world to play with, that you can see things down to a few kilometer scale. And so Pluto went from being an astronomical object to a world in its own right, thanks to the New Horizons spacecraft. And so what I really want to do is I want to give you two aspects of this discovery. The first is to give you a bit of the history, the background. How did we get to the point of sending a spacecraft to Pluto? And then in the second half, I'll spend some time talking about what we have learned about Pluto since 2015. And I should say, if you have questions, just stop me and ask in the middle. It's much easier if we have a conversation. Okay, so this is our playground. This is the outer solar system. There's Saturn, then you have Uranus, Neptune, and Pluto. And Pluto occupies the outermost region of the solar system, which is called the Kuiper belt. As you see, there are many Kuiper belt objects, of which Pluto is just the best known. Now, historically, none of these outer bodies were known. Uranus, not known to antiquity, but it was discovered by Herschel. So it was the first planet that was actually discovered rather than being known about since ancient times. And the story becomes interesting when people were looking at Uranus long enough to track its orbit, because it turned out that Uranus' orbit didn't do quite what was expected. And simultaneously, two people, Verrier in France, Adams in England, worked out that the irregularities in Uranus' orbit could be explained by there being another planet further out. There are endless disagreements about who actually came up with the idea first, but Galler in Germany used Leverrier's prediction, and he found a new planet in the first hour of observing. The prediction was that good. And so this was a triumph, right? That you take Newtonian mechanics and you can deduce the existence of a new planet without having seen it. So people watched Neptune for a while, and it looked at it as if Neptune had some irregularities in its orbit. And so Percival Lowell deduced that perhaps there was another planet beyond Neptune that was perturbing Neptune. And so he expended a large fraction of his considerable fortune building very big telescopes to look for this hypothetical planet that we call Planet X. He built a whole observatory, which still stands, but of course, to us now, he's more famous as the person who proposed that there might be canals on Mars. But he was very interested in looking for another planet beyond Neptune. Unfortunately, he didn't live to see it. It wasn't until 1930 that Pluto was actually discovered. Question? It was discovered by Clyde Tombaugh, always described as a Kansas farm boy. But you can see in this image that discovering Pluto was not trivial. This tiny little speck in the center here has moved relative to background stars here. And so because it's moved relative to background stars, that means it must be an R. So, but I think you'll agree that discovering Pluto is not an easy thing to do. Even though he discovered it, he didn't name it. The name was actually proposed by Venetia Burney, who was an English schoolgirl at the time. She wanted to keep the mythological tradition going in the outer solar system, And she also liked Pluto because the first two letters of its name recall Percival Lowell, who had originated the idea. So that seems fitting. Okay, so fast forward another 40 or so years, and it was discovered that Pluto had a moon, Charon. This is the discovery image, and again, you can see that this is not an easy case to make. But that little extra fuzzy blob there, Charon, just peeking from behind Pluto. This was discovered by Jim Christie at the Naval Observatory. And it was very soon realized that Pluto and Charon were actually in an interesting dynamical state. So Charon always presents the same face to Pluto, just like our moon always presents the same face to the Earth, right? But equally, Pluto always presents the same face to Charon. And so their two faces are always pointing towards each other. And so this is how the Earth-Moon system will look in a few billions of years' time. Eventually, the Earth will thin down until the Earth is always pointing its same face towards the Moon, and the Moon points the same face towards the Earth. So that's the dynamic state of Pluto and Charon. Percival Lowell thought that Pluto had to be very large because it appeared to be disturbing Neptune's orbit. It turns out that was actually an observational error. It wasn't true. When Pluto was discovered, though, it was estimated to be roughly the mass of the Earth. But as telescopes got better, people began to realize that Pluto was not even the size of Mars. It wasn't even the size of the Moon. It was really very much smaller than that. And so it was not massive, but as you'll see, it's still very. So this brings us to the late 90s. And the most significant event was that in 1989, Voyager 2 has to win some sort of durability award because it's still going. It flew past Neptune and Triton. And Triton is interesting because even though it's now a Neptune, it probably didn't start out that way. It was probably originally a Kuiper belt object, a bit like Pluto, that then got captured. And so the Triton flyby was our first good look at a Kuiper belt object. And it turned out to be extremely interesting. For one thing, it actually had geysers, active geysers jetting into space, which is totally unexpected. The post office got in on the act, highlighting the fact that Pluto had not been explored. And in fact, the discoveries at Titan got people so excited that they proposed a spacecraft mission to go and look at Pluto. In fact, this was a very ambitious mission. It wouldn't only go on to Pluto, it would then go on and try and find another Kuiper object. So in the NASA later things, a lot of effort and time was spent on designing this quite elaborate mission. And then in 2000, it was cancelled because, as these things do, it had gone way up. So that was a little disappointing, but through Byzantine politics that I'm not going to go into, NASA, which had begun to like doing things in a competitive fashion, ran a competition for a spacecraft mission in 2000. And in 2001, New Horizons, which is going to go to Pluto, was selected. And so as of 2001, we were pretty sure that there was going to be a mission to Pluto. The principal investigator is Alan Stern, and basically he has made Pluto his life's work. He started advocating for going to Pluto in graduate school, and he kept going. So he is a very persistent, and I would say quite scary individual. You wouldn't want to cross him, you really. So I joined the team very late in the proceedings, but one of the things I was given was a stub of pencil, a little like this. It's quite puzzling. Apparently, the idea is that you need to show the kind of dedication that involves you working your way all the way down to the stub of the pencil. So what did all that effort produce? Well, I should say, if you're interested in history, and like I said, there's actually a historian of spacecraft science who has written a nice story about how this actually happened. Anyway, so this is what the spacecraft was going to look like, and the scale is about the size of a ground pillow. You can see that it has a big radio dish because you're a long way from Earth, and so you need a big dish to actually transmit any signals. And then there are a bunch of instruments. The most important one, from my perspective, is the camera lorry, which is a very good long-range camera. And then tucked discreetly in the background where you can't really see it, power source, which is a lump of plutonium. So that's what the real spacecraft looks like. This is just before it was launched. You can see that it is covered in gold sheeting to help control thermal environments. And then in 2006, it was launched, and because Pluto is a long way away, it was launched extremely fast, 36,000 miles per hour. It took the Apollo astronauts 3 days to get to the moon. New Horizons got there in 9 hours, so it was really traveling. And this was the plan, that it launched in 2006, and then after not very much time, it would fly past Jupiter. And the reason for doing that is that it would get close to Jupiter and pick up some extra speed. So Jupiter gave it a big boost, and then there was a long haul out to encounter Pluto in 2015. So that was the plan. Meanwhile, on the Earth, things were getting a bit complicated. And I'm afraid to say that it's most of the fault of this guy, Mike Brown, who's an astronomer at Caltech. And what he found was that Pluto was not alone, that there were a bunch of objects out in the Kuiper belt that were quite large. And in particular, Eris turned out to be fractionally larger than Pluto. And there were a bunch of others that were, quite comparable in size. And so this created a problem because everybody's okay with 8 or 9 or 10 or a dozen planets, but the worry was that we end up memorizing a list of hundreds of planets. And so it began to be thought that maybe we shouldn't be calling Pluto a planet at all. And so the International Astronomical Union, in its wisdom, suggested that we should redefine Pluto as not a planet, but a dwarf planet. So they essentially put a motion that would demote Pluto from its planet status. And the resolution was passed. Now, this made quite a lot of planetary scientists annoyed because this is a bunch of astronomers dictating planetary scientists is what they call their planet. Nonetheless, it was passed. And so there was some reaction. Perhaps a large protest, but not. Even some cartoonists got in on the act. This is one of my favorite cartoons, the XKCD. But and I will say that when I on an airplane, the first question I always get asked whether Pluto is a planet or not. Okay, so this is a plot of New Horizons trajectory. So it went past Jupiter.
I don't know how.
Headed out towards Pluto. And when it got there, this was the plan. So it's important to understand that the spacecraft would come through the plane of Pluto and Charon at a fairly steep angle. Notice also that there are 2 little moons, as well as Charon, as Nix and Hydra. These were discovered in the interval between launching and actually getting there. And so the spacecraft would come through at a very sharp angle and then turn and look back towards the sun, and so it would pass through the shadow cast by Pluto and the shadow cast by Charon, because that's a good way of trying to see the details of the atmosphere. The other thing to notice is that, remember, New Horizons was traveling extremely fast, so this whole encounter takes, 3 or 4 hours. So you spend a decade getting there, and then the encounter lasts for 3 or 4 hours. So by 2015, things were starting to get interesting. These are pictures of Pluto taken at different times. And by around this time, we were starting to get images that were better than the best available Hubble images. And so you can't make any interpretations of this foretaste of what was going to come. And there was actually one early discovery that was unexpected, which is that Charon, the moon, turns out to have a pole that is dark. This was not known before, but it actually provided a very useful geographical reference, because when you get an image, you're not really sure what the orientation is. But when you see the pole, you say,
I'll be back on the deck. Out here. If you call me, I won't hear you because I'll be out there.
Sorry, somebody is speaking. I think that's Robco. I think that's you. Can you mute? So, July the 3rd, 11 days before closest approach, this is the image. And now you're starting to see things that we might like to interpret. Maybe this round thing here is a big impact crater. July the 4th, everybody's at their barbecues, and of course, the computer crashes. They had uploaded too many commands at once, and the computer threw a wobbly, and so a lot of people pulled out of their barbecues and set to work to try and fix things. Unfortunately, they did. So by the 6th, everything was back online, and this is Alan Stern, the project manager, both extremely relieved they still have a functioning spacecraft. July the 7th, you're starting to see this white region that became known as the heart of Pluto, its shape. July the 11th, 3 days to go. Maybe this is some kind of impact feature. Who knows what these weird things are, but you're starting to see, what might be actual geology. And then July the 12th was the last image we got until encounter day. Here is the heart again, and you can see there's all sorts of, maybe that's an impact crater over there. So on the day of encounter, this is a bunch of happy scientists at 1 a.m. watching the images come down. It takes 9 hours for the information to get from Pluto to the Earth. So there's always this enormous time lag. But here they are looking at the new images. And this is one of the first images we got. And there's the heart of Pluto again, this nice white area. So that's the raw image that came in at 1 a.m. By 1:30, bit of fancy image processing, you can really see how the details start to come out as I've looked backwards and forwards. And then at 3:30, we had this, which is a sort of false color image. They've added lower resolution color onto the high resolution visible image. And so that was just in time for press conferences. Here they are discussing the first results from the New Horizons flyby. One of the interesting things about being there was that all sorts of people came out of the woodwork. And so my particular favorite was this guy, Dr. Brian May, astrophysicist, who might be better known to you as the lead guitarist of Queen. So I occupied an office with Brian for a few days. And here are a bunch of very happy scientists looking at the first close-up images. The global images came down first, the close-up images came in later. And so here, with a little luck, is a video of a set of the close-up images. So I'm going to run this a couple of times.
So is the motion from the motion of the satellite, or is it from the probe, or the planet?
It's the motion of the spacecraft going past. Yeah. I mean, Pluto does spin. It spins pretty slowly. So this is just the motion of the spacecraft. Isn't that nice? And so one way of looking at this is that this discovery, this image, really concluded the first 50 years of space exploration, because by coincidence, the first image sent back from another planet was by one of the Mariner spacecraft on July the 16th, 1965. 50 years later, we get the first image back from Pluto. And so it's a nice sort of bookend of 50 years of exploration. So one way of summarizing this is through the post office. That was 1991. That was 2016. Pluto explored with a picture of spacecraft. All right. So what did we learn? Well, this is a Pluto and Charon in context. This is a picture of the icy bodies of the outer solar system to scale with the Earth's moon to give you a reference point. And so Jupiter has 4 big ones, Saturn has a big one and a bunch of little ones, and then there are Pluto and Charon, and there's Triton, Neptune's big moon. So one of the things that we wanted to do is to try and understand where Pluto and Charon fit in this rogues gallery. And so there are sort of general questions that we want to ask about any of these bodies. One is, what are they like on the inside? And in particular, is there an ocean underneath the ice? Because people get very excited about oceans because they start to think about, squid, things like that. We'd also like to know how these things were put together in the first place, because it turns out that's not actually an obvious question, or at least it's not obvious how to answer it. And then we'd like to make the link in their present day state and how they started. We want to understand how they evolved over time. And we didn't know a huge amount about Pluto before 2015. We did know it had an atmosphere, because you could watch what happens to stars as they go past Pluto, and the stars would get attenuated before they blinked out. And we were pretty sure that there was ice on the surface and rock in the middle. But one of the things that we didn't know was whether there was indeed a subsurface ocean or not. So one of the things that we didn't know is how big Pluto was exactly. We had a rough idea, but because of the atmosphere actually made it rather difficult to measure exactly how big Pluto was. Something else that we learned, we had no idea, is that Pluto is geologically active at the surface. There are bits of the surface that are extremely young, and so I'll show you examples of that. One of the other things that we did not anticipate is that Pluto has a nitrogen cycle, a bit like the water cycle on the Earth. On the Earth, the water evaporates from the oceans, it goes up into the atmosphere, it comes back down as rain and gets recircled. Something very similar happens on Pluto. There's nitrogen at the surface, it evaporates into the atmosphere, it gets precipitated back down, and then it rejoins the nitrogen at the surface. There's a nitrogen cycle. We think that Pluto probably does have a subsurface ocean, and Charon also likely had an ocean back early in its history, but that ocean didn't survive to the present day. So this is sort of a top 5 list of what we learned. What I'm going to do is to talk about each of these topics in a tiny bit more detail. So at some level, measuring the size of Pluto is not very difficult. You take your best image, you count the number of pixels across Pluto, you know the pixel resolution, and that gives you the size. In reality, it's slightly more complicated than that, but we came up with some pretty good numbers for both Pluto and for Charon. I led this effort, and I think this is going to be the one time in my career that an answer I produce is going to go straight into all the textbooks, right? Because now we actually know how big Pluto is. We found out that as far as we can tell, it's spherical. It's not distorted in any measurable way. So why does this matter? Well, this is just showing how dense various Kuiper belt objects are as a function of their size. And this is the situation that applied before Pluto. And in particular, you can see that the error bars on Pluto's density are pretty big. The error bars on Charon's density are a bit smaller. But what that means is that we couldn't actually tell whether Pluto and Charon were the same density or not. The error bar was large enough that we couldn't actually tell that. And so essentially what New Horizons did was it removed the error bars at this scale. And so we can now confidently say that Pluto and Charon really are different in densities. And so that means they're not made of the same stuff exactly. There's essentially Charon has less rock in it than Pluto does. The reason that matters is because we'd like to understand how Pluto and Charon form. And it turns out that there are basically two stories. One is that Pluto was sitting there minding its own business when something smacked into it and knocked a chunk of Pluto off that eventually became its moon. So this is the giant impact theory. The other theory is simply that both Pluto and Charon formed at the same time out of a bunch of, centimeter-sized objects. This is known as pebble accretion. So the important point about these two formation models is that they make different predictions about what the compositions of the two objects should be. If you're making everything out of pebble-sized objects, then everything should look the same. They should both have the same composition. They should have the same density. But if you have a giant impact, then the stuff that you knock off the surface of Pluto is going to be ice-rich. So in this case, Charon should have a lower density than Pluto, whereas in this case, Charon should have the same density as Pluto. Now that we have the measurements, that favors the giant impact hypothesis and not pebble accretion. So we can actually basically cross this thing out and say, this is probably what happened.
Neither of those gives capture as an option.
That's right, and that's because the probability of capture is very small. It's not. People rule it out on the basis of probability, but it could be a possibility. That's true. And in the case of capture, you would expect them not to have the same composition because it's unlikely to just happen by chance. We learned quite a lot about the global geology of Pluto. The interesting thing here is not so much the geology itself, naming conventions. Now, I've got to say that not all of these names have been approved by the IAU yet, but you can see some fun things are going on. In particular, if you're a fan of Tolkien, you'll see there's Mordor macula, Balrog macula, and then Lowell shows up, there's burning. And so you can see that people are having fun naming things according to various conventions.
Is that Lovecraft down there?
Cthulhu is Lovecraft. I suspect that the IAU will not approve that. Perhaps the most important one is Sputnik Planum or Sputnik Planitia. That's the big white area, the heart, that I'll talk about a little more in a minute. And here is a lovely global image with false color. This is Sputnik Planitia, heart. You can see that there's Charon. So this is a very odd picture because north is to the right. And so north is up here somewhere. And so this is our best global image. And you can see there's all kinds of stuff going on. There are impact craters, there are fractures coming across the surface. And I'll talk a lot more about this region in a minute. But this is aesthetic. This is a very pleasing picture. So one thing that we discovered is that some parts of Pluto are geologically active. Essentially, there's stuff happening now, and this was a complete surprise. This is part of Sputnik Planitia, and what you don't see anywhere on this surface is an impact crater. Normally, in the outer solar system, when you look at the surface, this is Ganymede. What you see are impact craters all over the place because it's been sitting there for 4 billion years, and so it just gets peppered with impacts. And so you don't see any of that on this surface. So this surface must be very young. Geologically speaking, it's probably only 1 million years or so old, which means it was essentially operating yesterday, as far as we can tell. So geological activity, nobody expected this. And the reason we think that it's geologically active is that there are two kinds of surface materials. You can see up here there are rugged, ancient terrain, lots of craters, and a sort of mountainous chain here. And as far as we can tell, this stuff is all water ice. Ice at Pluto conditions behaves like rock. And so you have rocky mountain outcrops that are very old. But then this white stuff down here, that is not water ice, but nitrogen ice. Pluto is so cold and nitrogen freezes out. And the nitrogen ice is the area where you don't see any craters at all. So the nitrogen area is young. The water highlands, the icy highlands are old. And if you look at the nitrogen plains, you see these funny sort of cellular patterns. And this was actually very exciting because a bunch of us on the team thought we knew exactly what those cellular patterns were. Because if you heat water and you look at it from the top, you see very similar cellular patterns. And that's just because the water is moving upwards and then cooling and moving back down. So you're seeing convection. The fluid is actually in motion. And so we're pretty sure that the nitrogen plane actually convecting, that it's in motion all the time. And that's why it hasn't accumulated any impact craters. And if you do some geological modeling of this, you can demonstrate that this actually works, that you're going to have an upwelling, and then the stuff will move along the surface, and then it will get sucked back down at these edges. And so this is a good way of explaining why this surface is so young, that it's continuously churning. Another complex surprise is that the highlands are cut by features. If you look at this area, it's blown up over here. You can see this sort of channel cutting through the mountains. And if you were on Earth, you would say, oh, that's a glacier. And so on Pluto, there are glaciers made of solid nitrogen, which is flowing down through the mountains out into the nitrogen plains. This is just another example. Here you can see it's bending around this curve, and then it's finally coming out into the nitrogen plains there. So this is partly why we think there's a nitrogen cycle, that nitrogen snows out onto the mountains, it accumulates in glaciers, just like on Earth, and the glaciers flow back down and deliver the nitrogen to the plains. Something else we see are fractures. On the Earth, if you pull two sides of an area apart, then you get faults developing, and the bit in the center will drop down. And these long linear features that we see on Pluto look exactly like that. They also look quite like the big canyon system on Mars. And so we're pretty sure that the surface of Pluto has been stretched apart at some point in its history. Something else we see, this is, it's not clear that this is right, but what you're seeing is an area of Pluto right at the edge of the imaging. It's getting bad down here because we're about to move into the shadow. But this is, on the right is topography, and the topography is pretty ratty. But what you're seeing is a mountain with these funny sort of pillow morphologies, and then it's a mountain with a hole in the middle. Now, a mountain with a hole in the middle on Earth, you would call a volcano, right? This is not made of rock, this is all made of ice. So some people argue that this might be a cryovolcano, so a volcano that's going to erupt cold stuff like ice, not molten magma. I'm not sure that's right, but I don't know how else to explain this particular feature. It's extremely puzzling. I talked a bit about the nitrogen cycle before, but here is just another example. So what happens is that we have this big plane of solid nitrogen, which is convecting, called splitting inertia. Some of that nitrogen evaporates, and then it condenses or it snows out onto the highland, and then it accumulates and it returns back to plains in the form of glaciers. So just like there's a water cycle on Earth, on Pluto we have a nitrogen cycle. There are very weird things that we don't really understand at all. This is something else you see in the nitrogen plains. They were nicknamed Bacilli for obvious reasons, but the important point is that the scale bar here is 10 kilometers. And these are pits. They're probably a few hundred meters deep, a few kilometers long. And so they're pits in the nitrogen. And we don't know what they are, but most likely there's something like these features on Mars. This is known as Swiss cheese terrain on Mars. And this is the polar cap, which is made of carbon dioxide ice. And so we think these things form by the sun evaporating the carbon dioxide off and carving these hollows. And probably something else similar is happening on Pluto, but we don't really know. Nobody really understands these objects. And then over here, we see there are these sort of, they're called blades. This is bladed terrain. And again, we have no idea what's forming these things. The closest analog that anybody's come up with is these bizarre features, these knife-like protrusions that you find in places like the Atacama Desert in Chile. These are called penitentes, and so it may be that these blades are giant versions of the penitentes, but again, nobody really understands it. Okay, we'd like to know whether Pluto has an ocean or not, and this is actually some work that I did a while back, and it's slightly complicated, but what you're seeing is time on the horizontal axis and distance from the center of Pluto on the vertical axis. And so you have a rocky inside and you have ice on the outside, and the colors come with temperature. And so what's happening is that the rock has some radioactive material, which decays, and as it decays, it heats the inside up. That's why the Earth is warm on the inside, it's the radioactive decay. So the inside heats up, it gets warm, and some of that heat gets conducted out into the ice shell. And so the ice shell warms up, and eventually it starts to melt, and so you form an ocean. And because there's enough radioactive heat in the inside, that ocean is quite happy to stick around 4 billion years, although you can see that right towards the end, it's actually starting to refreeze. And so you can generate an ocean from Pluto simply by radioactivity. There's one caveat. Here, I've assumed that the ice is not moving, it's just sitting there rigidly. If that water ice happens to be convecting, then it takes the heat out effectively, and so you don't end up with any ocean at all. And so on the basis of theory, we couldn't predict whether or not Pluto had an ocean, but we could use the observations to investigate whether or not an ocean might be there. And certainly an ocean is theoretically predicted as long as the ice shell is not convecting. So how can we test for the presence of an ocean? Well, one thing is that if the ice shell gets thicker, then it turns out you get surface extension. And the reason is very simple. So here's an ice shell, water underneath. If we freeze a bit of that water, ice expands, right? That's why your pipes break in the winter. And so if we take some of that water and convert it to ice, the total volume has gone up. And so in order for that to happen, the surface of Pluto has to move outward. Pluto actually has to expand as you convert water, which takes up less space, for ice, which takes up more space. Okay, so the surface has to move up, but you're doing that on a sphere. And so if you take a sphere and you try and expand it, then you're going to get extension. The sphere is going to have to stretch, and the way that extension, that stretching, is manifested at the surface will be some kind of fault, a fracture. And so if the ice shell is thickening, which we think is happening, you're going to get extension at the surface. Something else that happens is that the ice actually presses down on the water underneath, and if you press down hard enough, then some of the water might actually squirt out to the surface. And so that would be the way of explaining cryovolcanism, stuff shooting up to the surface as the water is getting pressurized. And then if you have an ocean, any bulge that you used to have, like the moon has quite a significant bulge, that bulge would disappear. And so you wouldn't expect to see a bulge if there's an ocean. And so, of course, now that we've sent a spacecraft there, we do see tension at the surface. We might see cryovolcanism, and we certainly don't see any evidence of a bulge. And so none of these are bulletproof arguments They do all point in the same direction. And there are actually other arguments too that I'm not going to go into that suggest there really was an ocean on Pluto that exists at the present day. So Pluto is probably an ocean world, and it's in good company. Here are the outer solar system satellites again, and now the ones in blue we think have subsurface oceans. So Europa, Ganymede, Pluto all have subsurface oceans, Enceladus does, Titan does, and we think Pluto does too. And so one of the lessons is that ocean worlds are really very common in the outer solar system. What about Charon? Charon is often unfairly neglected. But it's interesting. We see, like on Pluto, we see lots of big extensional features and rift valleys, a little like the rift valleys on Mars. This is the big valleys marineris on Mars, and you can see it bears some resemblance to some of the big rift valleys on Charon. So Charon certainly has a lot of extension. But Charon is small, remember, and so this is the same kind of plot that I showed you before, but whereas the heating in the interior of Pluto can keep an ocean going quite happily to the present day, on Charon, because Charon is smaller, it has a harder time hanging on to its heat. And so although you can form an ocean, that ocean doesn't survive to the present day. So we don't think that Charon is an ocean world now, but we think it probably did have an ocean deep in its past. So we found out how big Pluto is, which we didn't know exactly. We found out that Pluto is geologically active at the present day, and that was a complete surprise. Nobody expected that. Part of this activity has to do with the nitrogen cycle, which is that the surface supplies nitrogen to the atmosphere, which comes back down. We think that Pluto probably does have a subsurface ocean, and Charon had one in the past, but it hasn't survived all the way to the end. And of course, there was lots of other stuff that we found out too. So one question is whether Pluto is active, because we get excited about active objects because, in a sense, they're geologically more interesting. And certainly, it is active in the sense that it has this very young convective surface. But it may be that the inside is dead. The inside is probably still quite cold. And so the interior may not be active. There may not be Pluto quakes. There's almost certainly no plate tectonics. So you're seeing an active outside, but the interior of Pluto may be quite boring in the sense that it's not doing very much. Yeah, so it's probably not doing a whole amount in its interior. Sometimes you can appeal to tidal heating. So volcanic Io is very, very active because of tidal heating, but that doesn't work for the Pluto-Charon system. So I started out by posing these three questions. One of them was to talk about the internal structures of icy worlds. And we think that Pluto probably does have an ocean. Charon might have had one in the past, but not now. On the basis of the density difference between Pluto and Charon, we're pretty sure that Charon formed by a giant impact. And in terms of how they evolved, basically it was a slow cooling process. The ocean gradually refroze, and that's probably what causes the surface extension that we see and the cryovolcanism, if you happen to believe in cryovolcanism. So what happened next? This is just a departure image. As the horizons was going past Pluto, it turned back and looked towards the sun. And one of the things that allowed you to do was to see these lovely haze layers in the atmosphere. And so the atmospheric scientists had a field day trying to understand what these various haze layers are. You can also see the shadows being cast by the individual mountains. And there are the nitrogen layers. Well, after some effort, they managed to find a small Kuiper belt object that was accessible from the New Horizons trajectory. And so in 2019, they flew past it. It's called Arrokoth. And it's this very funny snowman shape, right? You can't actually tell it in this image, but it's not it's not merely a snowman, it's a very flattened snowman. It's almost like two plates that have been stuck together. And so we don't really know how this object forms, but it's interestingly very similar to some of the comets that we've seen. This is a comet with an unpronounceable Russian name that is also, it looks a bit like a snowman. And so this is telling us something about how this class of objects formed. Right now, people are still writing papers. This is a plot that I like. This is the number of papers about Pluto and Charon as a function of time. And I mean, what you can see is that this is 2015. And so, as you would expect, there was a spike in papers immediately after the encounter, but they're still carrying on at quite a high rate. And so people are certainly thinking about extracting the last dregs of information from the flyby. But of course, people have drifted away. There are new missions with more exciting data, and so people move away. There are some diehards who would like to put something into orbit around Pluto, which would be fantastic, but it is very difficult because you have to get really fast, you have to travel really fast to get to Pluto, and then you have to slow down in order to go into orbit. That's very difficult to do. So I don't think we're going to be around to see a Pluto orbiter, alas. Okay, let's wrap it up. I think it is safe to say that we did not anticipate how interesting Pluto was going to be. And what that's really telling you is that prediction is hard. It's just that the universe is better at making interesting things happen than we are at guessing what they're going to be. And so this is a lesson that we are bad at predicting things. I will say that, you know, this is essentially all down to Alan Stern. And so if you're willing to devote your entire career to making it happen, you can make a lot happen. And so he deserves a huge amount of respect for having more or less single-handed pushed this through. And then the outer solar system isn't that far away. And boy, there are a lot of interesting objects out there. And so I am hoping that this won't be the last time we've taken a close look at a Kuiper belt object. I would really like us to go and look at Eris or Haumea and their cousins. And so with that, I will end and take any questions.
Are there any questions? Yes. You have to repeat the question because people.
So the question is, what is the current status of Pluto as a planet? So it is not a planet. It is now a dwarf planet. And so there are only 8 planets in the solar system at the present day.
The dark spot. Describe it. Marking north. What does north?
Right. So the question is, why is the dark spot on Charon at the North Pole? It's a great question. And the answer is that the North Pole of Charon is very cold, as is the South Pole. And we think what happens is that dark spot is organic material. The organic material, it can sublimate and it'll hop around the surface. But when it gets to one of the poles, it's so cold that it just gets stuck there. And so it's a consequence of the fact that the poles are the coldest bit of the surface. Well, so the North Pole is the spin axis, and because Pluto is not very tilted, the spin axis is the bit that sees the least sunlight, and so it could be the South Pole. And in fact, you would not believe how much confusion there is about the coordinate systems, because halfway through the transit time, the IAU changed the longitude convention, and so somebody has written an entire paper pointing out all the mistakes that people have made in terms of lat and long. It's a disaster.
So we get 4 more questions. So there's one way in the back. Yeah.
What does nitrogen snow look like?
The question was, what does nitrogen snow look like? Excellent question. I don't know. I sort of imagine it's going to look like snow on the Earth, but I think the big difference will be that it will fall much more slowly simply because Pluto's gravity is so much lower. But I don't know.
And there's still one more in the back.
So you mentioned
Joel.
yes, in a different context than what we're now talking about. So there's a Planet 9 and Planet X that Brown and others are claiming as a result of analysis of perturbations or actually the orbits of some of these hyperbolic objects. What's the latest on that?
Right. So the question is, what about this Planet 9 that might be out there? And it's quite right that people have suggested there might be a big object out there on the basis of looking at the orbits of the Kuiper belt objects. People are burning a lot of telescope time looking for this thing, and nobody has found anything so far. And so I think people are starting to get a little disenchanted. But it's hard, this thing might be a long way out, and so it's going to be a very faint object. And so people are still looking, but I think the majority of people are quite skeptical at this point, is how I would put it.
Nancy?
Are there any other dwarf planets, or is Pluto the only one?
So Eris, which is what precipitates, sorry, the question is, are there other dwarf planets? So Eris, which precipitated the whole crisis, is as big as Pluto, and so that's certainly a dwarf planet. And there are probably a couple of other Kuiper belt objects that are dwarf planets. And then some of the biggest asteroids by the IAU definition also qualify as dwarf planets. So there are, 5 or 6 that we know about.
What is driving the convection if the interior is cold?
So the question is, what is driving the convection if the interior is cold? Maybe I misspoke. The interior it's lukewarm. I wouldn't say it was cold. And basically it's radioactive decay. There is still heat leaking out. And it turns out that solid nitrogen is extremely soft. It flows very readily. And so it actually doesn't take much energy to get it to turn over.
You mentioned earlier in the talk that Charon had an ocean and then refroze, and then that came back. And you explained in part by the fact that Charon is so small. I don't know how so small in relation to other small things, but I wonder if you could say more about that dynamic. I mean, if that's something that our oceans would be produced, for example.
Okay, so the question is about the survival and freezing of the ocean on Charon and how that relates to us. So what's happening with us is that the sun is steadily getting more luminous. And so I don't remember the details, but I think there's probably going to be a point in Earth's history, a few billion years from now, when oceans won't be stable on the Earth any longer. That doesn't really matter at the distances of Pluto, because the sun is essentially negligible. You don't get any significant heating from the sun. And so for Pluto and Charon, it's all about the radioactive decay in the interior, maintaining the oceans inside. Does that help?
Yeah.
So Barry, are there questions on the chat?
I asked, I haven't, say one more thing.
Okay, to the people on Zoom, any of you have questions? This is your chance. I'm not seeing anybody jump in.
Yeah.
When Joel paper recently saying that wildlife radioactive isotopes fluorine used to create heating in the first core heart. Can you exclude that as a source of heat for Pluto and some of the other planets?
So the question is, what is keeping Pluto hot? And the answer is no, it's exactly that. We think that it's the uranium and thorium and potassium in the rocks inside Pluto that are keeping it warm. Now, we don't know that that's true, but we have a pretty good idea of how much radioactive material was around in the earlier solar system. So we're just assuming that Pluto got its fair share of that material.
I'm curious about this surface and what are the heights of the features
You obviously can see shadows, at least in some cases. And I assume you can figure out where the sun is coming from. You get a good idea of what the height of the features are.
Yeah, so the question is how
Substantial, I'm just curious.
the question is how big these features are, and you're absolutely right. Some of these mountains are 4 or 5 kilometers above the plains, and so Pluto is really quite rugged. Maybe so comparable to the Sierras, right? 15,000 feet is 5,000 meters, and so the sort of topography that you see in the Sierras is comparable to the topography on Pluto.
So you have any ideas about the formation mechanism?
That's a good question. How do these mountains form? Not really. Well, actually, that's not quite true. So why is there that big nitrogen plain there? What we think happened is that is probably the scar of an impact. So something came in and dug a hole in the surface of Pluto, which then got filled in with the nitrogen because the nitrogen flows to the low points. And so the mountains around it are probably the jumbled rock left over from that big impact. That's probably the best explanation.
The others? Well, thank you again.
Thank you.